Imagine standing beneath a machine taller than a skyscraper. Above your head, a steel beam weighing hundreds of tons slowly rises into the air. No explosions, no dramatic effort, no visible struggle, just a massive structure, floating upward with astonishing precision. At first glance, it almost seems impossible. How can a machine lift something heavier than a blue whale without collapsing under its own weight? How can a crane balance enormous loads while standing on a relatively small footprint? And perhaps most surprisingly, how do operators prevent these giants from simply tipping over? Because when you look closely, cranes appear to violate common sense. The heavier the load becomes, the more impossible their work seems. Yet every day, around the world, giant cranes build skyscrapers, assemble bridges, construct ships, install wind turbines, and move components weighing hundreds, sometimes even thousands of tons. Without them, modern civilization would look completely different. This is the incredible engineering that allows giant cranes to perform what often feels like industrial magic. The problem with lifting heavy things, humans have always faced the same problem. How do you move something too heavy to carry? Ancient civilizations solved this challenge using ramps, rollers, pulleys, and sheer manpower. But as structures became larger, those solutions became insufficient. Cathedrals, skyscrapers, ports, factories, modern infrastructure demanded something entirely new. Machines capable of lifting extraordinary weight. But lifting is only part of the problem. The real challenge is stability, because weight creates force, and force creates danger. Imagine holding a heavy object at arm's length. The farther away the weight moves, the harder it becomes to control. Eventually, your body simply cannot maintain balance. Cranes face the exact same problem, except instead of holding a suitcase, they may be lifting hundreds of tons. And instead of risking a sore arm, they risk catastrophic collapse, which means every crane is constantly fighting the laws of physics, every second, every lift, every movement. And the secret to winning that fight begins with one of the most important concepts in engineering: balance, the secret of counterweights. At first glance, most people focus on the load, the steel beam, the shipping container, the turbine blade, the giant concrete section. But engineers focus on something else entirely: the force trying to pull the crane over. Because every weight hanging from a crane creates a turning force called torque. The farther the load extends from the center of the crane, the stronger that force becomes. Without a solution, the crane would simply tip forward. That's where counterweights come in. Massive blocks of steel or concrete positioned behind the crane. These counterweights create an opposing force, a balancing force, a force that allows the crane to remain stable. It's surprisingly similar to a seesaw, except instead of balancing two children, engineers are balancing hundreds of tons of industrial equipment. The result is a machine that appears almost effortless, but behind that effortless appearance lies a carefully calculated battle between competing forces. A battle measured down to the smallest detail. Because when hundreds of tons are involved, there is no room for approximation. Some crane counterweight systems weigh more than entire houses, but balancing weight alone isn't enough, because even the strongest crane must transfer those forces somewhere, and that brings us to the ground beneath it. The foundation that nobody sees, one of the most important parts of a crane, is often invisible: the foundation. When a giant crane lifts a load, the force doesn't simply disappear. It travels downward, into the structure, into the supports, into the earth itself. A weak foundation can turn an engineering masterpiece into a disaster, which is why crane installations often require extensive preparation. Engineers analyze soil conditions, ground density, load distribution, environmental factors. Everything matters, because a crane capable of lifting hundreds of tons becomes useless if the ground beneath it cannot support the stress. In some projects, the foundation takes longer to prepare than the crane takes to assemble. Massive concrete pads, deep support systems, specialized reinforcement, all hidden from public view, yet all absolutely essential, because every spectacular lift depends on something remarkably simple: a stable place to stand. For some mega projects, the invisible foundation beneath a crane weighs far more than the crane itself. And yet, even with perfect balance and perfect foundations, another challenge remains. How do you actually lift hundreds of tons into the air? The power of cables and pulleys? The answer isn't brute force, it's mechanical advantage. One of the oldest engineering principles ever discovered. Giant cranes rely on sophisticated systems of pulleys and cables. These systems distribute force across multiple points, reducing the amount of effort required to move enormous loads. The principle sounds simple, but its impact is extraordinary. way. A properly designed pulley system allows cranes to multiply lifting capability dramatically. The machine doesn't fight gravity directly. It works intelligently, using physics to its advantage. Steel cables become the muscles of the crane, massive winches provide controlled movement, hydraulic systems contribute immense force, and together, they transform impossible tasks into routine operations. A load that appears impossibly heavy to a human observer becomes manageable through engineering. It's not magic, it's mathematics, and it works every single day. Some crane cables are strong enough to support weights that would crush ordinary vehicles instantly, but lifting a heavy object isn't enough. The real challenge begins when precision becomes critical. Moving hundreds of tons with millimeter precision, imagine lifting a massive steel section weighing hundreds of tons. Now imagine positioning it with extraordinary accuracy, not within a meter, not within a few centimeters, but sometimes within millimeters. That's the reality of modern construction. A bridge segment must align perfectly. A turbine component must fit precisely. A skyscraper element must connect exactly where intended. There is no room for guesswork, and this is where crane operators become extraordinary professionals. They must understand load behavior, wind conditions, swing dynamics, visibility limitations, and machine response, all while coordinating with teams on the ground. Every movement must be deliberate. Every adjustment must be controlled. Because when loads become enormous, small mistakes become expensive very quickly. What appears from the outside to be a slow operation is actually a highly complex dance between machine, operator, and physics. Some crane lifts require months of planning for operations that last only a few minutes. And nowhere is that complexity more visible than in the largest cranes ever built. The giants of the crane world. Not all cranes are created equal. Some are designed for construction sites, others for ports, others for offshore platforms, and some exist specifically to handle the largest objects humans have ever attempted to move. These mega cranes push engineering to extraordinary limits. Tower cranes dominate city skylines. Crawler cranes move through giant industrial projects. Floating cranes operate at sea. Port cranes unload enormous container ships. Each design solves a different problem. Each reflects decades of engineering evolution. Some rise hundreds of meters into the air. Others lift weights so large they challenge imagination. Watching these machines work can feel surreal. Tiny workers move around structures larger than buildings. Massive loads rise slowly against the skyline, and physics itself seems to bend before your eyes. But every movement remains governed by the same principles: balance, force, control, and precision. The larger the machine becomes, the more important those principles become. Some of the largest cranes ever built can lift loads weighing thousands of tons in a single operation. Yet perhaps the most remarkable thing about cranes isn't their size, it's what they make possible. The machines that build the modern world look around any modern city. Skyscrapers, bridges, power plants, ports, factories, wind farms. Almost every major structure owes part of its existence to cranes. Without them, construction would slow dramatically. Infrastructure projects would become far more difficult. Entire industries would operate differently. Cranes are rarely celebrated. They rarely appear in headlines. Most people pass them every day without giving them much thought. Yet they are among the most important machines ever created, because they solve a challenge that civilization repeatedly encounters: moving the unmovable, lifting the impossible, turning ambitious ideas into physical reality. Every skyline tells part of that story. Every bridge, every port, every industrial facility. Behind each one stands a crane, or many cranes, quietly doing work that once seemed impossible. At first glance, a giant crane appears simple, a machine lifting heavy objects, but beneath that simple image lies one of the most elegant applications of engineering ever developed: a machine balancing enormous forces, distributing weight with extraordinary precision, transferring stress safely into the ground, using cables, pulleys, hydraulics, and mathematics to overcome gravity itself. Every lift is a demonstration of physics in action. Every successful project is proof of human ingenuity, because giant cranes do far more than move steel and concrete. They make modern civilization possible, and perhaps that's what makes them so fascinating. Not merely their size, not merely their strength, but the fact that they allow humanity to build things that would otherwise remain impossible dreams. Which crane fact surprised you the most? The counterweights? The foundations? The giant cables? Or the incredible precision required for every lift? Let us know in the comments.